Okay, so in this video, we're going to do some examples, more examples of indefinite integrals, and then also introduce how to do definite integrals with U-substitution. So the example we're going to start with says use substitution to find the antiderivative of the integral of z times the square root of z squared minus 5 dz. So remember that whenever we have an integral, or if we're trying to find the integral or we're trying to find the derivative of, we like to change our roots to fractions. To fraction exponents, remember. So remember that the square root is equal to the power of 1/2. So these two things are exactly equivalent. And now, if we want to use U-substitution, remember the first step is to choose U. So remember, we want U to be plugged into another function, so the obvious choice here is to choose z squared minus 5. Right, so we're going to let U equal z squared minus 5, right? Then du dx, right, the derivative of this, we get just 2z, right? And then that becomes du is just 2z dx. Now we have a problem. Hopefully you have identified it, because du is equals to 2z d. Oh, this should not be x, because remember our original variable in this example is not x, it's z. So that was a silly mistake, silly typo. Right, but we still have the problem that I was talking about, because right here our du has 2z dz, but we only have z dz left, right? There's no 2 there. In the integral, we only had z dz, right? So there was no 2, right? No number 2. But we can easily fix that, right? So what we do is, right, we multiply du by 1/2 to get rid of the 2. Right, so we have du is 2z dz. Now I'm going to multiply both sides of that by 1/2, and that's going to become 1/2 du is equals to z dz. Right, so when we go to replace the z dz in our integral, right, we have to replace it with 1/2 du, right, not just du, right, because du had this too. Okay, so let's do that. So let's bring down where we were. So right now we're here. Right, so the second step now is to plug in u and du. Right, so we have, this is the integral that we're working on, and right, we can rewrite this again, right? We can move the z over if that helps you see it, what we're doing, right? So we can have the z dz all together, right? So then the z squared minus 5, that's our u, and then the z dz, that's our 1/2 du. So I'm going to plug those things in. So this becomes the integral of u to the 1/2 times 1/2 du. I don't like how this looks like a z. Okay. And then now what? Remember, if we have a constant multiple in our integral, we could pull that out. That was a property. So I'm going to pull out the 1/2, and then I have the integral of u to the 1/2 du. Right, so constants, remember, constant multiples can be pulled out. Okay, so now we get to just do the power rule on this, right, which is super nice, right? So we leave the 1/2 on the outside, and then, right, 1/2 plus 3, that becomes u to the 3/2, and then we divide by the new exponent, and then we have plus c. Right, and so then remember that we don't divide by fractions, we multiply by their reciprocals. So I just flip the denominator over to bring it out of the denominator. And then 1/2 times c, right, like I have to distribute this to both terms, but c is any constant, and 1/2 times any constant is still a constant, so we just keep it as c. And then this becomes 2/6 u to the 3/2 plus c, right, with that simplifies to 1/3 u to the 3/2 plus c. And then remember, oh, I forgot to write a step in here. Right, so the third step, just so that you guys have the steps written within, the third step, what we did was integrate using antiderivative formula. And then the fourth step now, after we did that, is to plug u back in. So now it becomes 1/3, and then what was my u? My u was z squared minus 5 to the 3/2 plus c. So that is the answer to our question, right? The integral we were trying, indefinite integral we were trying to solve. Okay, so that's the first example. So like I said, let's do one more example of indefinite integrals, and then we'll talk about definite integrals with U-substitution. So the second example, use substitution to evaluate the integral sine of t over cosine cubed dt. Right, so I always like to, I think sometimes it helps to rewrite things in a simpler form. So, you know, right, realize that this is sine of t over cosine t cubed. Right, and so then, right, when we're talking about, like, you can also write this as sine of t, move it a little bit, over times 1 over cosine t cubed dt. Right, and then remember, if we have exponents in the denominator, we could always bring those up by making it a negative exponent, if that helps you see it better, right? But I think we can see it right off the bat that what's plugged into something else is cosine, because that's cubed, right? That's plugged into x cubed, and right, and then sine t is just sine t, it's just there. So, oops. So I'm gonna let my u be cosine of t, because I know that's what's plugged into x cubed, right? Because it's cubed. And then the du, remember the derivative of cosine is negative sine, right? So again, right, we can multiply both. We only have a positive sign in our integral, so we can multiply this by -1 on both sides, and that will give us just positive sign. Right, so when we take our integral, right, which we said is, I'm going to just flip these over just to help with you guys seeing it. So this is cosine. Remember, it doesn't matter what order you multiply things in, so we could just flip it. Right, so then this becomes u is cosine, u to the -3 times, and then, right, sine of t, that's equals to negative du. So I'm able to just plug in negative du. Right, but remember, this is not subtraction, this is multiplication by a negative. But remember, if we multiply, right, there's an imaginary 1 here, so if we're multiplying by -1, we can just pull that out to the front. So I'm going to take out that constant multiple, right? So pull out constant multiple of -1, right? And I'm pulling it out of the integral, but I just keep it right up front. And now I'm able to just integrate this with respect to u, use a power rule, right? So that becomes, I add 1 to the numerator, so -3 plus 1, that's -2, and I divide by the new exponent, which is -2, and then I have my plus c, right? So then notice, right, if we have a negative times a negative, that becomes positive, so this is just u to the -2, oh, let me move down, So this is u to the negative 2 over 2 plus c. Right, and then remember, we can get rid of negative exponents by bringing that down to the denominator. So this is really 1 over 2u squared, right? I'm bringing the u to the negative 2 down, so now it becomes positive 2 exponent. Right, and then now I can just plug back in my u, which remember, our u was cosine, so this becomes 1 over 2 cosine squared of t plus c. So that is the answer for this integral here. So I hope you see how what we're doing is literally just replacing stuff in our integral that's given to us with u stuff, and then that makes our lives easier, right? Like when we got to this step, to simply just use the power rule to get the integral. And that is the general idea behind u substitution. So now let's talk about substitution for definite integrals. Substitution for definite integrals. And remember, what's a definite integral? Remember, that's just an integral that has bounds in it. So given, basically, well, what we have to be, it's basically all going to be the same thing, right? So remember that u substitution, the form is we have some function f with some function g plugged in times the derivative of g. The only thing that's changing, right? And so then what we did was we replaced the g with u and the g prime dx with du. All that's changing is now we have bounds. And remember, right, we're letting these, remember that when I first introduced definite integrals, right, these values here are x values, right? So like x1 is a and x2 is b. Those are x values. But now we're changing those x values, right? Because now our formula is not with respect to x, it's respect to u. So we have to change them to become u values. So what does u1 equal and what does u2 equal? Well, remember, u equals g of x. So g, right, g is the formula that takes an x and makes it a u, right? We're plugging in x into some formula g, and that gives us a u. So if we want to find what u1 and u2 are, right, we have to plug in a into g, and we have to plug in b into g. Okay. So let's do an example. And I'll talk about later how you can avoid all of this, right? So use substitution to evaluate the integral from 0 to 1 of x squared 1 plus 2x cubed to the 5th dx. Right, so when I'm looking at this function, I know x squared itself is a function, right? So that's not being plugged into anything. This is the more complex piece. So 1 plus 2x cubed is being plugged into x fifth. So what I'm going to do is let I don't know where that came from. Let u equal 1 plus 2x cubed. Then, right, we do the derivative of u, and what's that, right? 1 is going to go to 0, the derivative of constant is 0, 2 times 3 is 6, and then subtract 1 from the exponent, right? So du is 6x squared dx. Okay. And then, right, we have a problem again because in our equation we only have x squared dx left, right? And then we have this 6 in here. So we have to address the 6, right? So remember, we used that same technique we used in the last example. So I'm just going to multiply both sides of this by 1 over 6, right? So that's going to be 1/6 du is x squared dx. So now since we have our formula for u, right, what we can do is also, right, we also need to change the bounds from x values to u values. So, right, I'm going to plug in, our bounds is 0 and 1, so I'm going to do x is 0, right, then u is equals to 1 plus 2 times 0 cubed, right, and that's just 1 plus 0, right, because anything multiplied by 0 is 0, so that's just 1, And then when x is 1, right, that's going to become u is 1 plus 2 times 1 cubed, right? So 1 cubed is 1 times 2 is 2 plus 1 is 3. So then, right, plug u du and u bounds in. Right, so our integral, which was 0 to 1 of x squared, wait, let me rewrite this. This is x squared 1 plus 2x cubed to the 5th dx, right, that's going to become, right, the x is 1 became 3, and then the x is 0 became 1, and then, right, we have is 1 plus 2x cubed, so that's going to become u to the 5th, and then we have 160u is x squared dx, right, so that's going to become times 1/6 du, right, and I can pull out, because I'm multiplying by 1/6, I can pull it out of the integral. Okay, and now everything's in terms of u, so now I can integrate, right, use the power rule right on that, simple enough, so that becomes u to the 6 over 6, and then I have to plug in 1 and 3. Right, so remember the 1/6 is outside of our integral, so we have to do the whole definite integral. We have to plug our bounds in before we multiply this through. Right, so this is going to become 1/6 times, right, I'm going to plug in 3, so I get 3 to the 6 over 6 minus, now I'm going to plug in 1 to the 6 over 6. 3 to the 6 is 729 over 6 minus 1 to the 6 is just 1 over 6. So this just becomes, right, 1/6 times, right, these have the same denominator, so we could subtract it, so that becomes 728 over 6, so that's 728 over 36, right, which we can simplify. They're both even, so I'm going to divide by 2. That's going to become 364 over 18, and those are still both even, so let me divide by 2 again, so that's 182 over 9. So that is our final answer to this definite integral here. So remember, definite integrals, right, ones that have limits of integration or bounds of integration, right, numbers in there, always end up as a number. Okay, so let's talk about another way you can do this, right? So either you can transform the bounds into u bounds and plug them in for u, excuse me, or you can keep them as x bounds and wait until you turn the equation back into x equation to plug in the bound. So I'm going to do that in the next example, the second technique for definite integrals. So whichever floats your boat. So use substitution to evaluate the integral from 0 to 1 of x e to the 4x squared plus 3 dx. Right. So off the bat, we know that one of our basic functions is e to the x, so we know 4x squared plus 3 is being plugged into this exponent, so that's what I'm going to let be my u. So I'm going to let u equal 4x squared plus 3, right? And so then when I do the derivative of that, I'll get du is 8x dx, right? But we only have x dx here. There's no 8. So again, I'm going to multiply now this both sides by 1/8, and that's going to get rid of that 8 on the side. So now I'm going to just proceed with my original integral, and I'm going to plug in u and du. Right, so technically we have to write like u of 1, because technically these are u's now, because I'm changing everything to be in terms of u, is e to the u times 1/8 du. So I'm just putting these bounds in here as placeholders, just because technically, right, leaving them at 0 and 1 is incorrect, but it's not that big of a deal. So I'm going to pull out my 1/8 because I'm multiplying by it. I could pull it out. Times, oh, I already pulled it out, sorry. And then now I can integrate that, which remember we know that e to the u, its antiderivative is just the same, right? E to the x derivative is e to the x. So antiderivative of e to the x is just e to the x. And then I have to evaluate that at u of 0 and u of 1. But what I'm going to do instead is I'm just going to change this back in terms of x by plugging my u back in. So this becomes e to the 4x squared plus 3. And then I have to evaluate that at the x values 0 and 1. So this becomes 1/8. And then I have e to the 4 times 1 squared plus 3 minus e to the 4 times 0 squared plus 3. Right, so that's 1/8, and then this becomes 1 squared is 1 times 4 is 4 plus 3 is 7, e to the 7 minus e, and then 0 squared is 0 times 4 is 0 plus 3 is 3. Okay, and that is, right, our final answer. So basically, for definite integrals, right, this is equal to some number. You can put it in your calculator. So for definite integrals, because they're always equal to a number in the end, right, that's why I wanted to emphasize that. You have the option 1, change the bounds / limits of integration, let's call them x1 equal to a and x2 equal to b into u values by plugging in x1 and x2 into u equals g of x. Plug in the new values as the bounds into u. Right, so basically like you're turning them into u values, so you don't end up, when you do it this way, you don't end up, right, you don't plug, right, the equation u equals g of x, right, in this case was 1 plus x squared. Remember, normally we would plug this back into our equation to change it back in terms of x, but what we're doing is we're not doing that. Instead, we're just going to change the bounds into u values and plug them directly in for u, right? I plugged in my new bound 3 into here, and then I plugged in my new bound 1 into there. That was the first way. And then the second way is that you don't plug in the bounds until after you integrate with respect to u and plug the equation u equals to g of x into the answer, right, whatever you get when you integrate. So you don't plug the bounds in after you integrate with respect to u and plug in the equation into the answer to get it back in terms of x, and just plug in the original x value or whatever variable you're given to bounds. Okay, so that's it for U-substitution.